Welcome to the CITRIS seminar today. Also welcome to our web viewers at Davis, Merced, and Santa Cruz. Today, as part of the CITRIS People and Robots Initiative, we are hosting Adam Coates, Director of Baidu Research Silicon Valley AI Lab. Adam and I should go a long time back. Adam and I were both students at Stanford working on autonomous helicopters in Andrew Ng's group at the time. Adam did an entire PhD thesis worth of work on helicopters, but called it his undergrad work, and then moved on for his PhD to kind of endeavor into deep learning, where he's made a lot of breakthroughs. He's one of the first to really kind of start noticing how it's more the amount of data and just time that influences the performance rather than maybe some algorithmic details. At Baidu, he's been leading the team that's developed deep speech, state-of-the-art deep learning speech recognizer for Mandarin and English, as well as he's been making a lot of progress in a different effort on deep learning for driving. And I'll leave the floor to Adam.
Well, thank you. So yeah, actually, thank you guys. I'm really excited to be here on behalf of Baidu and the really great team in the Silicon Valley AI Lab. Actually, the autonomous driving work I did back at Stanford, and deep speech is a product of the AI Lab. So our mission in the AI Lab is to develop hard AI technologies that let us have a significant impact on the lives of hundreds of millions of users. So this sort of scale of impact that we want to have has really forced us to think pretty hard, because there are a lot of problems that we could work on in AI, but we wanted to think about what are the ones we could make progress on, where a big leap, a breakthrough in performance would be something that mattered a lot to like 100 million people. So I'm going to throw some sort of factoids at you that kind of influenced our thinking about this. So of course, Baidu's home market is in China. But in China, there are about 600 million mobile netizens. So China is an economy where mobile is taking hold very rapidly. And about 90% of internet users actually have a mobile connected device. And in fact, laptop and PC use is at the same time declining. Many people say that their mobile device is their preferred connection. And especially for new people coming online, it might even be their only connection to the internet. They might, in fact, their mobile device might even be the first internet-connected device they've ever owned. The second is that e-commerce and online to offline is growing very rapidly. So all these services that let you use your online technologies in your mobile device to do things in the offline world that also give you this very rich interaction are becoming incredibly popular. And users are building up very sophisticated behaviors to interact with all of these services. And then the third one really caught our eye, which is that because of these trends, accessibility is a huge challenge. You have many people who've never owned a device like this before. Many of them don't know how to type in pinyin in order to put in Mandarin characters. And so even if many users are connecting to the internet for the first time, they're already starting to deal with these accessibility issues. And you start to see things like really huge phone screens that people are talking on because they're trying to cope with all of these accessibility problems. So the thing we decided would make a huge impact in this world is if AI, instead of just making autonomous cars and robots and personal assistants, could actually make devices more useful and understandable to people. We wanted it to be as natural for someone to interact with the very first device that they own as it is for them to just talk to a person and interact with them, something that they already know how to do. So in the past, I would have said that this was something we couldn't make progress on very rapidly. I'd have said this was a pretty tough goal and might have left it to people working on HCI or user experience design or something like that. But I think because of deep learning, because of the progress that we can make in speech recognition, natural language, computer vision, I think AI has a huge chance to address this problem in a new way. So the first step that we've decided to take in this direction is to try to develop a new speech recognition system to really solve the problems of speech interaction, to develop a speech system that is as natural to interact with as a human is. And there are a lot of hurdles to actually doing this. Obviously, if you use technologies today, they get about 1 in every 20 words wrong. And we already know how this works, because if you talk to your friend on a flaky phone connection and it drops 1 in every 20 words, you hang up and you say you'll call them back later. So we already know that this is just not good enough. And there are all kinds of other hurdles like noise, poor microphones, and heavy accents that you have to deal with in order to really solve this. So if we want to solve all of these problems, we have a lot of powerful tools with machine learning. And so to give you some idea for how machine learning has worked in the past, I wanted to go through a sort of cartoon example of how you might build a speech engine. So let's suppose that I give you a bunch of little audio clips like this. So these are like little audio waveforms taken out of something recorded from a microphone. And I'm going to painstakingly label them with the International Phonetic Alphabet of what sound you're hearing there. Is it a B or a M sound? And then, hopefully, you can go pick your favorite machine learning toolkit. Maybe you use scikit-learn or something. And you would train a predictor that, if you give it little snippets of audio, could actually predict that this is me saying, what time is it in Beijing? And then you could convert that into a transcription. So it would be beautiful if this worked. This is the nice cartoon. In practice, it's really not this straightforward at all. And this is one of the reasons that speech recognition has been very hard to get working. And so the only way that we've had to make progress in the past is by sort of injecting these other stages into the system. So if you wanted a machine learning algorithm to work really well, you can't just pipe this audio into it or pipe a spectrogram into it. You have to insert these other modules and then kind of engineer them to change the data around so that the system will perform better. And what this gives us an opportunity to do is to take all of our prior knowledge and experience about the world, sort of stuff them into the algorithm so that maybe it will perform better the next time we run it. And so if you get very good at this, if you become an expert in speech recognition, you can actually get something like this to work reasonably well, but it is a ton of effort. You can spend entire PhD theses developing systems like this to get them to work well. So this is actually a perfectly reasonable idea, but it's also a gross oversimplification of a real traditional speech system like you might be using today. The first stage in these things is usually to compute some features based on the audio input. And then the next stage is what we would call an acoustic model, kind of like what I was just showing you, where you try to predict what sound you're hearing at each moment of time. And then the next step is to take all those little sounds that you predicted and combine them into some kind of state sequence that sort of keeps track of the beginnings and ends of sounds and how they fit together. And then from the state sequence, you need to merge this with all kinds of linguistic knowledge about how words are pronounced, the different kinds of pronunciations that are okay for certain words, as well as a language model for which words are likely to be with which other words. And then finally, that will give you a transcription. So this is a far more complex pipeline, and so it shouldn't be that surprising that it's really hard to get this working, and it's also very hard to improve it for a particular application. And so it's a totally reasonable thing to do, to break the problem down and try to solve each of them. And what we do in practice is each of these involves machine learning itself. So the acoustic model might be a Gaussian mixture model. The sequence model could be a hidden Markov model. And we have some n-gram language models at the end. We sort of try to fuse all of these together to get a high-performing system. And kind of like in the example of feature engineering, this is where we kind of get the opportunity to take all of our own knowledge that we've gained about language, about how people speak, and how sounds work, and fuse them into the structure of the system to try to make the problem easier. So this sort of runs into a problem, though, which is that if I give you more data, and I give you more computing power, things that we're getting more and more of all of the time, each of the machine learning algorithms in that system will get better and better, but then it'll eventually hit a plateau in performance. It'll turn out that if you give me more data or a bigger computer, it just doesn't perform any better. I don't get more accurate speech recognition. And so the result is that if I want to go, if I find myself out here, where I'm not getting any more performance from more data and computing power, the only way to get better performance is to expend all of this expert engineering effort. So most of the progress on this problem is actually coming from this kind of heavy engineering and really sophisticated systems. So as an example of why this really gets you, I want you to think about what kinds of speech you're likely to hear if you have 100 million people trying to talk to you for all of the things that they might want you to do. So for example, you might have a bunch of users in an office in one of your little data sets, and you can tune your algorithm and work really hard on it, and you'll get your speech engine to work pretty well and serve all of those office users, and they'll be happy for a while. And as your system becomes popular, people will realize that they suddenly want to use it in the car for their Maps application or to send a text, but it won't work for them because suddenly there's noise, the acoustic environment is different. People would like to talk to their phone when it's actually far afield rather than holding it up to their mouth. And now this is a totally different environment that you haven't tuned for. And so a very common thing to do is to specialize your engine, come up with new parameters, new models, try to fuse them all together, and specialize it for this new case so that all of these users are really happy. But you can see how this goes wrong, right? Once we start worrying about accents, for example, if I need to have a separate engine for people with an Indian accent and an American accent, now I have to have 4 different scenarios, and this can really explode if I'm trying to deal with many different combinations of users. And so it will work for a while, but it takes a lot of resources, a ton of expertise in order to make this work well. So I actually have a friend who has an Italian accent, and speech recognition drives him bonkers because it works for everyone around him except for him. And he can ask for something very straightforward where everyone in the room knows exactly what he said, but the system will just ignore him. And so until someone goes to the trouble of trying to make one of these systems work well for him, it's very challenging to see how that problem gets addressed. So this is really something that's falling through. Like, we want this to work for everybody. If there are hundreds of millions of people out there who are using this for the first time on their mobile device, we want it to work for everyone all the time, no matter what they use it for. So how is deep learning actually going to help us get around this? I think one of the reasons that deep learning has become so popular is because of scalability. That deep learning has a very different behavior from all of these machine learning algorithms that we've been using in the past. So previously, if I put them all together and I get more data and computing power, my system doesn't improve and I have to start doing this specialization. One of the reasons deep learning might be different is that when you have very little data and a very small model, it doesn't work that well. But if I have a lot of data and a really big model, deep learning performs better and better and better. And so one of the things that we've been thinking a lot about at Baidu is, what if we put all of our effort or a great deal of emphasis on getting more data, building much more powerful models to try to solve a problem like this? Maybe that will give us a way to get around all of these engineering difficulties and really get to a goal that we care about. So in fact, some people have tried to include deep learning in the speech recognition pipelines, and this actually did make a big difference. So what folks have done in the past is taken deep learning, basically a neural network, and replaced one piece of the pipeline. So in this system where I have to take a little clip of audio and predict a sound that will go into my sequence model, I'm welcome to actually use a lot of different algorithms. And so when deep learning started to become popular, it turned out to be very useful to replace this predictor with a neural network, and the whole system actually got a lot better. And so effectively what happened was that the overall system started performing better, and we sort of ended up on this new curve, where for a little while, if you gave us more data and more computing power, we could get a little bit better without actually re-engineering the whole system. So that was really great, but we still have this huge scaffolding around our system. And so we sort of wondering, if scale and computing power and data are the things we care about, is it possible to do much better by just training all of the parts together? Is that the thing that will give us new levels of performance? So in effect, what we want to do is replace most of that pipeline with deep learning. And in a lot of our experiments, we still have a language model in here because we can train it from a huge amount of text off the web. but it's actually much simpler than we would need otherwise. It doesn't include anything like pronunciations or stuff like that that an expert would need to give you. And so this is very exciting to us if we can pull it off, because if you have thick accents or people who differ in how they pronounce different words, you could actually learn some of those things from data and not worry about whether it's in your system or not. So why do we actually think that this is going to work? The hope is that if we were to replace this whole system with deep learning, remove all these components, maybe that would let us get onto yet another curve, where as we add more data and computing power, the speech recognition system will get better and better over time, and we can actually reach our goal. So how do we actually make this work? So here's a sort of simple first version that you might try. So this input down here is an audio spectrogram, right? So I take my audio waveform that I recorded on a microphone, and I just convert it into this little frequency domain representation. So it's a simple transformation. And then each of these little neurons here represents a deep neural network, which is just going to try to predict straight from the audio which English character it is hearing. And this seems kind of crazy, right? Because we know that like C and CH and K and KN, all of these things can have different sounds. But we're going to try to do it anyway. And so hopefully, if this were working well, and I say, what time is it in Beijing, we'd really like the first few neurons to predict that I'm saying W here, and I'm saying H over here, and then it's allowed to insert some blanks to make the timing work out until it transcribes what time is it in Beijing. So obviously, knowing whether I'm saying H here or an A relies on context. I can't figure that out from just looking at a little tiny snippet of audio, because I need to know how to spell and all of these things. So in fact, rather than just a deep neural network, we use a recurrent neural network, which is kind of a fancy way of saying that we add these horizontal connections so that neurons out in the future that are looking at the end of the audio are allowed to sort of capture some stored information from the neurons that are looking at the past parts of the audio. In practice, though, you can just think of this as a very giant sort of deep neural network that has a special kind of connectivity. And effectively what this does is all the characters way down at the end are being given a way to sort of see what's going on here at the beginning to help decide which character they're actually hearing. So in order to actually train this, we have a special cost function called CTC that was created in 2006 by a team in Jürgen Schmidhuber's lab. And the CTC cost function gives us a way to compare these character outputs to a ground truth label that a human has given us. So if this is my recurrent neural network, and I try to predict that this is Adam saying, what time is it in Beijing? But this network makes some mistakes. It outputs the wrong characters at some places. The CTC cost gives us a way to take the ground truth transcription that a human has given us and then give a score for how close our output is to the correct transcription. And once we have this objective function, we can actually update our model. We can use the backpropagation algorithm to tune all of the weights in this big neural network so that hopefully the next time I give you the same audio clip, you actually get a closer transcription. And if we do this over and over and over again, we will hopefully make progress on the problem. So this is an approach that's been tried before. So the CTC cost function that I just mentioned was actually created back in like 2006. So this idea has been around for a little while, but it wasn't nearly as good as the top speech systems. So if you compared this method to a production engine or a state-of-the-art speech system, it didn't work as well. And so we had a hypothesis for why that might be. What we thought might be going on is that maybe end-to-end deep learning ought to work better. Maybe it will work better. But the problem is that back in 2006, we didn't have enough data or we didn't have a big enough model. We just weren't at a large enough scale yet to see this work. Maybe what happened was we were down here on this part of the curve so that even the traditional systems looked a lot better. But if we could somehow find our way to a point further down the curve, it would actually perform better. So if we actually wanted to pull this off, there were two huge problems in our way, one of which is that we needed a lot more labeled speech. So you saw in the training algorithm that I had to have the ground truth transcription in order to update my model. And those transcriptions have to come from people, and getting those transcriptions is really expensive. So that's one problem. And the other one is that these very large models have like tens of billions of connections in them if they're very large. And so to actually train them quickly so that we can find a good model is a huge problem. So for the data, I'm actually going to talk about the English data set first. We trained this system from almost 12,000 hours of raw audio. And to give you a sense for how that compares, if you look at sort of standard academic speech recognition systems, they're usually trained on some popular public data sets. One's called Fisher, another one called switchboards, like people talking on a telephone, and also people reading the Wall Street Journal. So these have like 80 hours for the Wall Street Journal data, maybe up to 2,000 hours for the Fisher data. And so deep speech, right from the beginning, we went to the effort of capturing a data source where we had about 12,000 hours total of raw audio. So we trained up the system. We actually found that it still didn't perform well enough. So we use a common trick, which is to synthesize even more data. So it turns out synthesizing more audio data is straightforward to do, because if I take some background noise or some sort of distracting audio, and I just add the two waveforms together, I get another perfectly good audio clip, but where I can hear someone talking with background noise. And so even though the transcription is the same, it's not quite as good as hearing a new person with a new sentence, I do get unique audio, and I can learn how to deal with noise that way. And so with this synthesized data, we have something like 96,000 hours of unique audio, almost 100,000 hours of unique audio that the system gets to hear by the time it's done training. The other problem, as I mentioned, was that we need large models. It turns out that we need to run a lot of experiments in order to find a good model. We have to think about how many neurons there are, how tall the network should be, how many different layers there ought to be, and so on. And so a typical experiment takes something like 10 exaflops. So I think it's 10 to the trillion billion. Well, you can work out the exponent on the end of this. There are a lot of zeros that should be out here that go off the slide. In practice, if you want to run this on one GPU, it's going to take one experiment, something like 3 to 6 weeks with a very, very well-optimized implementation. In practice, it might actually take longer because you run out of memory. So if we want to be able to iterate quickly in order to make progress on this, we have to have a way to train these models faster. Because the thing that gates progress in machine learning applications is this cycle from having an idea about a new model that might work to being able to code it up and getting your results. And if it takes 3 to 6 weeks to go around this cycle just once, it will take you a year before you get anything working. So thankfully, we have a systems team that has been working hard on solutions for this. So of course, GPUs have become very popular in deep learning because a typical GPU will have something like 6 teraflops of single precision floating points, 6 trillion floating point operations a second. And it'll still take you 3 to 6 weeks at that rate. And so we need a lot more computing power in order to make this practical. And so we've been working pretty consistently with anywhere from 8 to 16 or more GPUs for a single training run. So for a rough idea, that's between like 48 and maybe up to about 100 teraflops of single precision performance. And all of these have to be connected by a high-speed network so that they can work tightly together on this optimization problem. So if you just want to do this and you throw all these together in a box, it turns out it's not enough still. In order to exploit scale effectively, you also have to do a ton of hard systems research and engineering. So for example, we're using optimized reductions that are about 20x faster than the ones in open source MPI code. So if you go online and download OpenMPI to run on your cluster, it will have an all-reduce function that lets you grab all of the updates from your models on different GPUs and add them up so that every GPU gets the complete update from all of your data. And that code is about 20x slower than what the team has developed. And the reason I want to point this out is because one of the things we're noticing is that there are all kinds of frameworks out there for deep learning, but one of the things that matters most for scale is to really squeeze out a lot of performance from the hardware you've already got. Because as you go to more and more GPUs, your scaling problem gets harder and harder and harder. And so one of the things we've been focused on is delivering very, very fast libraries and components to make these training systems work well. And in fact, you can get one of them online. So that CTC cost function turns out to involve a quite expensive forward and backward algorithm that actually takes a lot of effort to run on the GPU. So the team built a highly optimized version called Warp CTC that if you're working on a problem like this, you can actually download yourself. So if you do all of this work, you can actually train models in about 3 to 5 days. And I think these models, in fact, are even bigger than the ones we started with at the beginning. So, and for the systems hackers out there who thrive on such numbers, the sustained performance of something on 16 GPUs is like 50 teraflops, and it's very close to about 50% of peak for a lot of jobs. And that's the end-to-end efficiency of the system. So this is a really key enabler. If you want to be able to run hundreds of experiments, get them all back, and be able to decide what to do next quickly, a lot of this effort turns out to be really crucial. So how does this actually perform? There are a lot of benchmarks in the speech world, but it's really hard to compare them, in fact. So it turns out that state-of-the-art production systems, as we mentioned, tend to be specialized for applications. So if you just use the engine on your cell phone, or you go try to use an off-the-shelf engine that was optimized for a particular set of customers, and you throw it at your favorite test set, it probably won't work that well. And so it's a little unfair to benchmark against them. Meanwhile, a lot of the research systems that are out there that you might see in a research paper are often heavily tuned to the benchmark themselves, because handling the full breadth of all of the audio in the world is so challenging. So instead, what we decided was that since our goal is to make devices as natural as people, we wanted to compare with actual people. So that if you were launching an application tomorrow, you guys will have a sense for where is speech technology today compared to what you could easily do with this person sitting there listening to the phone. So in this case, people is either untrained crowdsourced workers, like from a crowdsourcing service where they just listen to the audio and try to type the transcription for you. Or we even tried using like a committee of our own researchers who've been sitting there and listening to all this data for a long time and have become quite good at transcribing. So for English speech, we tested this out on a whole bunch of read speech data. So these data sets involve people sitting there with like a copy of the Wall Street Journal or a common book and just reading it to you. And you see how accurately you can transcribe it. So the blue bar here is Deep Speech 1, which was the first revision of this system that we started talking about last December of 2014. And the red bar is actually Deep Speech 2, which is sort of the latest incarnation of this idea. And on the vertical axis is the error rates, the percentage of words you're getting wrong. And the big thing that we found here is that Deep Speech 2 is actually quite competitive with these human crowdsourced workers. So it used to be, maybe a couple of years ago, if you wanted to launch a service where you were going to transcribe a bunch of audio and you had to do it, crowdsourcing might have actually been a reasonable thing to try to do for accuracy. But now, with deep learning algorithms scaled up enough and enough data, we can actually produce a speech engine, totally data-driven, that's competitive with those same crowdsourced workers. So we think this is a good milestone along the way. It turns out you can also get test sets with very heavily accented speech. And again, getting closer to human, I think on a lot of these cases, we're still a little bit behind. But on things like Indian accents, for example, that are even challenging for human workers who are working in the United States, the system is actually getting very close to what a human worker can do. And what I want to draw as a distinction is that the big differences between Deep Speech 1 and Deep Speech 2 are not fundamental algorithmic differences. there's a lot of work to find the best models, a lot of work to capture new sources of data, a lot of work to make the system faster. But the fundamental idea of this end-to-end data-driven deep learning framework is actually the same between these two. And this phenomenon shows up in a lot of places of deep learning. As we get more computing power, more data, and run a few more experiments, these numbers keep coming down. And so we really believe we're on a trajectory to do this.
So for the humans, I mean, what kind of mistakes do they make? Is it because they need to type really quickly, or is it?
There isn't a time limit. Because they're sort of paid by the utterance, I think they're incentivized to go a little bit quickly. There is a bit of quality control on it. They're usually transcribed more than once. A lot of the common problems, as I understand, come from like noise and heavy accents. Like you can even see in this data, right? The humans do much worse as you increase the accent. So most of these workers are living in the United States. So you can see that for, say, an American or Canadian accent, they're down around 5% word error. So we figure the number of just kind of dumb mistakes is probably less than 5%. Yeah, Kurt?
And how much neural network architecture development is between DS1 and DS2?
Quite a bit. So the number of experiments is really large, and we're only able to do those because we have enough computing power and all the optimization. If you look at the models, they're all in the Deep Speech 2 paper that I can give you guys a link to. The models are not, hugely different, but the devil is always in the details. So one thing that we discovered, for example, is that in order for these models with only backward context to work, they can only see the past audio in order to predict the character, you have to give them a small layer that looks at a little bit of future context in order for them to work well. And the only way you discover that model is by running lots of experiments, looking at all the things you're not doing well with, and thinking about what you could tweak to the model that would give it the power to make the right prediction. And so those discoveries take a lot of iterations.
Let me just, you mentioned a few slides back that you were still like 3 days to train a model?
Yeah, it depends on the size of the model, but yeah, on the order of days.
But I'm guessing you're not happy with that.
Well, never. There is a phenomenon in that I think researchers have a sense for what they are willing to tolerate. And so if the systems team works extremely hard and produces this beautiful scalable system that cuts it down to 1 day, everyone will show up with a 3x larger model or 3x more data and say, look, guys, look at all the great performance we got now. And they're back to the 3 to 5 day timeline.
Is there at least one person in the organization who's trying to figure out how to require less compute or less communication?
It's something that we're looking at, yeah. There are lots of ideas coming out of the systems research side and the machine learning research side, thinking about how to make the models smaller, sparser, et cetera, to try to make it run better on hardware, both for training, but also for deployment, which is another thing I can talk about. Yeah.
Transcription error rate might be 1 unit, but how about comprehension? I
Yeah.
presume that the error rates might be much lower, right?
So I'm not going to talk about in this talk actually understanding what has been said and understanding the difference between sort of a small nuisance error and a serious semantic error. That's outside the scope of the transcription, but in our vision of making devices as natural to interact with as people, this is something we want to tackle. Yeah?
So one of the distinctions you guys make in your 2014 paper in this talk is that you run character level encoding instead of like phenome level, if I understand correctly.
Both of them are character level.
And I'm just curious, would you apply to Mandarin and like Cantonese? I don't quite see how the character model will still hold out. You need so it's just like emphasis on the tones.
Right. So next slide. Good segue. So because this is data-driven, we can actually avoid this because we don't have phonemes in the system at all. As I said before, we're taking English training data where we have audio spectrograms, and then we just have this training algorithm that is learning to predict the transcription directly in the native character set. And so if we want this to work with Mandarin, the obvious thing to do is to give it now Mandarin audio that looks the same, but use a Chinese character set. So to do this, the set of changes is surprisingly superficial. We do a lot of cross-validation search, look for models that happen to perform better one way or another, but the basic training system is the same. We just change our output layer to have about the 6,000 most common Chinese characters. And then you can also include digits, Arabic numerals, and English characters, because it turns out hybrid speech is really common in Mandarin speech. And also, we had about close to 10,000 hours of Mandarin data, kind of like our English set. And then we also have a language model trained from a whole bunch of Chinese language text. So that system that is essentially the same as the English engine. For short query-like utterances, things quite a lot like the training data, this system is actually better than a pretty solid human. So what we did was we took a couple hundred utterances, got them labeled by people in our own group, and then we had a native Mandarin speaker sit down, listen to them all, and transcribe them, and we compared them to Deep Speech 2. And it turns out that Deep Speech 2 is actually superior to that single human working by themselves. So we were sort of shocked by this. And when we first started to see this level of performance, Tony, who leads our Mandarin speech team right now, would take his headphones off and look at me, and he'd say, "Adam, I have no idea what this person is saying." So I don't know what the transcription is. And then he says, "But I look at the ground truth now that was created by a committee of other people." He says, "I'm not sure about that, but when I look at what deep speech says, I'm really sure this is the right answer." And so it's this shocking phenomenon that this system can now give you a transcription that you couldn't figure out on your own, but you're actually quite confident is the right thing once you see it. And so we even did another test after this with some fresh data, since some people had already seen the other test, and tested it against an actual committee of native speakers transcribing this. And it turned out the data was a little bit easier this time, but deep speech and the committee are really neck and neck. And this is all data-driven. It was a system developed on English by a team that has only a handful of Mandarin speakers. So I think this is really emblematic of the kind of power of these sorts of approaches. There's very little language-specific knowledge in there. So with modest changes, this works really, really well. And one of the sort of fun things that I always like to call out about this is that the system actually automatically learns to handle simple hybrid speech. So it's actually really common for people to ask for famous people in their queries, or to say something like iPhone. It's a popular brand name. And so if I say, my favorite singer is Angela Baby, the engine will very happily switch character sets and just start transcribing in English when it hears these words. And that's all just falling out of the data. So there were a lot of reasons for skepticism at the outset of this. This was not a sure thing. There were a lot of concerns that we heard that, is there really enough data? Can you get enough data to make this work? Can you train the models fast enough? It takes so long to train one model. How are you going to find one that actually works? Will this work in Mandarin, right? It's the first thing a lot of folks ask when we say we're developing in English. They say, you're at Baidu. How is it ever going to work in Mandarin? And then, of course, a big question for us was, can this ever be as good as a human? Does this approach have any hope of reaching our goal? And I say we're doing really well on all of these, tentatively getting quite close to what humans can do, at least in certain verticals. So the last big thing is, I've been talking all about training, all about sort of the results of the system, but of course we want to actually have impact with real people. And we want to be able to take these giant neural networks, put them in the cloud, and let people use them every day. And so a big question is, how on earth do we deploy these things? So we've trained these. We want hundreds of millions of people to be able to connect to it. But there is a problem, which is that the natural thing to try to do is use GPUs. Right? We use GPUs to train them. We know they're great for deep learning. Why don't we use GPUs? The problem is, the GPUs, the hardware is optimized for throughput. They're optimized to take huge amounts of work and grind through it very, very quickly in a batch. But users actually care about latency. They don't care about all the other data you're trying to process. They care about their one little snippet of audio getting transcribed and coming back to them right now. So GPUs are really not efficient for this case. They're not good at handling these little batches all by themselves. And the way to think about that in terms of systems is that if I try to evaluate my neural network on one little clip of audio, I wind up doing a lot of matrix vector multiplications. And this is very inefficient for the hardware. So what the team did is actually developed what we've been calling batch dispatch. So if you think of all of these arrows as being audio packets coming into the server from different users, then what the system does is it has a scheduler that tries to pick out audio packets that are coming in at close timescales to one another, combine them all into a batch, and then go back to using matrix-matrix multiplication so that we can handle a whole bunch of users all at once really efficiently. And so it turns out that if you have a whole bunch of concurrent users, maybe dozens on a single server or a single GPU, the latency is actually really great, competitive with a lot of production engines. So the last hiccup to taking this technology to hundreds of millions of people with deployability, we think this is going to work out pretty well. So to sort of wrap things up, I'm super excited that deep speech is actually catching up to human beings. We're not there yet. There's a lot more to do. There are definitely a lot of verticals and a lot of scenarios where humans are obviously better than machines still. But we think there's a chance that this approach can scale up to meet that. And in the sort of query-like scenarios we've been working on, we think we're already there. And of course, if we want to make an impact for real people, these large models are really great for performance, but we think we can also put them in the cloud, which is a big hurdle out of the way. And so the reason that we're sort of on this mission is that we really want to make interacting with technology as easy as interacting with people. Make it so that all the technology that we already have, all the features that we've already got on our phones are accessible to everybody. And we want to do it not just for the people that happen to speak like we do with the same accent or whatever, but we want it to work for everyone all the time, wherever they are, whatever application they want to use. So thank you all very much for listening. And if you are also excited about this sort of mission to build great AI technologies and also to try to have a significant impact on hundreds of millions of people, definitely come talk to us or send me an email. Thanks.
I think we still have some time for questions. You want to kick people out?
Sure. We're on the site.
Thank you so much for this. This is very exciting. I'm an English teacher, and I teach reading. I'm a reading specialist. And one of the issues that we saw in your time visit in Beijing is that WH is a consonant blend. And my question is, does your model adjust for consonant blends for things like diphthongs and both OA combination?
Yeah.
Is
So
that
sort of
something that can be done?
Right. So the system does not explicitly try to handle this. We haven't taken our own knowledge about how these work in English and baked it in. Instead, the neural network is being forced to essentially learn how these things work on its own.
I see.
So you're right that WH is something that there's no way to describe like how that's supposed to sound with a single character. The system has to look at enough audio context to figure out roughly what the word is and then back out the correct spelling, having seen lots and lots of examples.
Similarly, do you have a thing in your model for dropped or sounds that are not pronounced? For example, in pneumonia, P is never pronounced, or in castle, T is not pronounced.
Right. So one common thing you'll see is if you take away the language model. So there's a language model that's trained on a huge, huge text corpus. So it has a giant vocabulary, bigger than any one person. If you hear a word and you look at just what the neural network thinks was said, if it's a very uncommon word, one of our favorites is Tchaikovsky, right? Something that's probably not in your audio, and it's some terrible, long etymology for how this name got created. But it's very hard to sound it out. But what you'll see is the network actually thinks the most likely transcription without the language model is very phonetic. It'll be like, CH something. And so for something like pneumonia, it might get it right if it's heard that word a bunch of times. But if not, it'll often just give you a phonetic spelling. And then when you add the language model to it, it'll recognize that there is a word, pneumonia, that starts with a P that the model thinks is reasonable, even though it didn't think it was the best one. Yeah.
Thank you very much for the talk. It was very interesting. And I was wondering, how did you come up with the network architecture in the end? Like, did you just have to try different architectures, or was there kind of heuristics that you could apply?
Yeah, this is, I think this is sort of one of the dark arts of deep learning, or at least it has been in the past. Getting the first system working is always a challenge. Once you've got something that doesn't explode, which is its own sort of problem, the thing that we rely heavily on is being able to try a wide range of possible networks that we think might be helpful, based on looking at the literature and what other networks are popular, and also sometimes based on our own knowledge of like what the system is having a hard time with. And then we launch all those on the cluster, check how much error they get on a sort of held out set of data, and choose the best one. And you can kind of have a survival of the fittest thing going on, a guided exploration that gets you to a great model.
And just to have a guess, how many layers have you in the network and how many nodes?
It's all guided exploration. You'll run an experiment, you'll see, oh, the system got a little bit better when I added a layer, and then...
No, I mean, like the one you use in the end, like how big is the network, just to get a number?
We tried a whole bunch. The current state-of-the-art one that is not in the paper, I don't know. In the paper, I think it's typically like 2,000 neurons in a layer, something at that scale, and anywhere from like 3 to 7 recurrent layers, depending on the experiment. So that's the rough scale. Let's start over on this side.
Hi, thanks for this talk. I was wondering how you collect all of that. Where are you getting that?
So a lot of it is just transcribed. We have a big pile of audio, and you can have people sit there and actually just transcribe it. We've also done read speech, so you can have crowdsourced workers. You can just show them a sentence and have them read it to you. That's really inexpensive because reading is fast, and then you have the transcription. We've looked at a whole bunch of different ways of sort of capturing data, but a lot of the obvious ones you might think about, like found data on the web, it's challenging to get those to work, but there is a bunch of data out there.
Have you explored using something like text-to-speech as like the tools to the problem in order to generate more data and then eventually have both systems work better together?
Yeah, I think, I have to ask Ryan, one of the researchers in the lab actually did try something like this. Synthesis is always a little tricky because on the one hand, you can synthesize an unlimited amount of unique sentences, but usually only a small number of voices. So what will wind up happening is you have a speech engine that's just really good at recognizing that synthesized audio. And one of the things that I think is really great about the Mandarin engine is that it has a huge diversity of speakers in the data sets. If you look at common data sets online, or sort of benchmarks that we use, the number of unique people that you see in the data set is small. And so for the algorithm to learn the full breadth of how people say things is really hard for those cases. Yeah.
I wonder if there's some value in thinking about a strategy for fixing it once it's deployed, so that in particular by taking advantage of the fact that a lot of people who talk funny in the same way with a particular accent. And those people may have, for example, if it's an interface to government services or something, or gambling or something, a high incentive to get it to work better. And they could coordinate and volunteer to give some of that backdrop information for these cases that weren't really adequately sampled.
Sort of like being able to correct like transcriptions for
Right. So your Italian friend will hook up with other Italians and fix it.
Yeah, there's actually, so, you know, handling a lot of these communities where there's an accent or something that's not common. This is actually a big problem for developing economies, right? You tend to have pockets of people who have an accent or even a dialect that's kind of their own. So one of the challenges of this system is how do you get those folks into the mix? In some sense, machine learning is quite democratic this way, in that it optimizes for what's represented in the data. But I think working on like low resource scenarios and getting people to provide data, I agree that's a thing we'd love to do if we can find a way.
We've passed one. Let's take the other questions offline. Thanks, Adam.
Thanks, Pete.